Okay, so let's see how we are formalizing this as a mathematical problem and how we can use maths and optimization and machine learning to get to discover that, these principal components or main directions that we want to project our data on to preserve the maximum information are the eigenvectors of the covariance matrix of the data. Why we have that. So now we will understand everything, and hopefully all the pieces will fall into place. So let's start with this. So as in any machine learning problem, what we have our training data, X. So each row here represents a sample. So we have n samples with n d-dimensional samples. So we have d dimensions. The next step, as you guys recall, what we need to do is we need to compute the covariance matrix based derived of our data, right? And next, the next step would be to do the eigen decomposition of this covariance matrix, or what we call to use the SVD. So I'm not going to go into details, but you guys feel free to read about the mathematical background of SVD and how it works. But basically, the SVD gives you directly all the eigenvectors of the matrix, okay, and their corresponding eigenvalues. That's all that we need to know. So, giving our covariance matrix sigma, we get two things here after doing SVD. We get two outputs, U, which is a matrix that retains or that basically puts all eigenvectors in columns. Okay, so each column of matrix U is a principal component, okay, or like an eigenvector in this case. And for each eigenvector, we have its associated eigenvalue, okay. So here what we have our for each dimension, basically we have an eigenvector. So here for now it's a D by D matrix. So we will understand why it's a D by D matrix. So the next step would be to transform the data X into a new space where new features are created or extracted, okay? And these features will be stored in a matrix T, in a new matrix T called the transformed data. So let's look at this. This sums up everything. So here what we have our original data X, right? Its dimension is n times d, and then we have the new basis U, right? So this is what we call the basis of the new space, or the eigenvectors. So each column in this matrix is an eigenvector, okay, eigenvector, and it has its associated lambda, okay? So if this is the ith eigenvector, so this should be lambda I, and this guy right here, it should be the vector mu I, for example, okay? Right? So we stack all the eigenvectors, and then what we do, we multiply. So when we multiply X by U, what we're creating is a transformed data. We're transforming the data using all eigenvectors. So this is actually the projection that we're looking for. So we're projecting the whole data on each of those directions, like, first principal component, second. So we're projecting our data along different dimensions. How many dimensions here? D dimensions, okay? So if you know this, the output, the size of the output, here it's n times d and d times d, so the d will just disappear. We'll have an n times d transformed matrix. So this is just basically projecting the data, okay, our data, on all eigenvectors. Why we're using all eigenvectors? How many dimensions we have originally? We have d dimensions. Here, what is the number of my eigenvectors? How many eigenvectors here? D eigenvectors, okay? And here, D is actually, the other D is the dimensionality of the components, the elements, or dimensionality of the eigenvector, elements of eigenvector, okay? So, right. Now, what do you guys notice for the matrix T? Did we reduce the data? Sorry? We did not reduce the dimensionality. That is very good. So if you look at the matrix D, it has exactly the same dimensionality as X. So by using these eigenvectors, by just doing these projections, we still have projected, originally we have D dimensions, and we projected on also what? D dimensions, okay? So in this case, we have exactly the same number of dimensions or the same number of features. And if we go back to the very original case right here, so let's look at this. So when we had the data, what we did exactly is we just projected the data onto two different axes, right? But nothing has really changed. We just extracted new features or new coordinates. So we transformed the data. So it's very clear in the first example. So the data in the beginning was located right here. And then what we did, we rotated it, and it's just, a transformation of the data. Okay? Right? So let's go back. So here, this is not what we want. So it's good we extracted new features. So if I look at this example and I tell you, what is this doing? This is just describing the data in a different way. This is very important. This is a new representation of the data. Okay? We can call it a new representation of the data. Okay? Or also, we extracted new features because right here, these features are different. They're not the first one. And this is, from the first example that I saw of the houses. We lose the feature once we project it. Okay? Great. So what is the next step? The next step is that we want to perform dimensionality reduction. So how to do that? So here, U is basically we need to order U, the vectors, all these column vectors, by increasing values of lambda, of their eigenvalues. So for example, let's say in this original matrix, the first eigenvector, this vector, has a lambda 1 equals to 10. And then the third eigenvector, okay, has a lambda 3, okay, equals to 25. So in this case, if this is the maximum value, the maximum eigenvalue across all eigenvectors, then we should take this one as the first principal component, PC1, okay? So basically, we are simply ordering all eigenvectors by, decreasing eigenvalues. So we take the largest, and like the second component will be the one with the slightly smallest, etc., etc., okay? So after doing that, so we select the first top K. So here we select the first top K eigenvectors. So here it should be by, right, so let's look at this. So next, to perform dimensionality reduction, I introduce a new matrix UK. And here I have all my eigenvectors, right? But I select only K, the top K. So remember, the dimensionality of the eigenvector has D elements, okay? So that's the number of features. But here, what we now have is only K elements, okay? So I select K dimensions or features. So what does this mean? It means maybe in the beginning, in my space, I have 1, 2, 3, 4 dimensions. And then I'm just projecting onto, so D equals 4, and then I'm projecting onto K equals 2. So this is my first component, and this is my second component, okay? That's what it means. We're selecting the eigenvector. So now, next, let's see how this will change, and this is the best part here. So, right, we map the original data using the selected top K eigenvectors with the highest eigenvalues, right? And these are also called principal components. So now we want to not only map the data as before, but we want to map and reduce, okay? So we want to also reduce. So this is a new component here. How to do that? So there are a few changes in the dimensionality. So the D here, we need to change the number of what? Of the bases of the on which we're projecting. These are the number This is the number of PC, of principal components. So we had before, what did we have? We have D. So this should get reduced to K, right? So what we will do is like, oops, we will reduce the number of dimensions by selecting only the top K, right? Eigenvectors with the highest eigenvalues. Now, what is the dimensionality of the transformed data? So we're multiplying n times d and d times k. So here, the transformed data will be n times what? K, very good. So here, basically, we have succeeded to reduce the dimensionality of the data and after we projected it. So the t here, if we move everything, so we're going to have also k. And right here, we will have our k. So this is basically a new, we can say, describe the data in a different way, in also a lower dimensional space. Okay, because now we have performed dimensionality reduction. Okay, great. So now it's very simple. So you guys get it. So we have our data. We estimate this from what? From the covariance matrix of the data. So this guy, the U, all the eigenvectors were derived from the covariance matrix X transpose X of the data. Okay, so that's how we got the principal components. Now this is quiz time, so guys, pen and paper, and this is a good quiz for to train yourselves and see whether you really got the meaning of PCA and also connected with your previous knowledge on regression. So let me read the questions for you, and I will give you 5 minutes to write the questions down. So the first question is, does PCA change the original data in terms of local structure? So what is local structure? It means that two close points in the original space will remain close in the PCA space once we do the projection. Yes or no? This is very important. So if you illustrate it, you should be able to answer this if you remember what we did. Now the second question is, what is the difference between linear regression that we saw in lecture 6 or the least squares minimization, okay, linear regression, and PCA? Now the third question is, well, these should be multiple options, right? So let me just put it this way, A, B, C, D. So does PCA decorrelate the data features, B, enhance the correlation between data features, preserve the correlation or dependencies between features, or preserve the maximum variation of the data? And if you like just use a few examples, right? Remember all what we have seen from the beginning. If you were attentive, you can intuitively answer those questions. Okay, guys, I would like you to try, even if it's not, very straightforward for you. Just try, make drawings, right? So you know what is correlated data, decorrelated data, all those things. So the first question, you can see it from here. It's quite simple. All right, you cannot read. Right. It's maybe not clear. My writing is not very clear indeed. Yeah, sorry about that. Yeah. So I can read it again. So does PCA change the original data in terms of local structure? Or put simply, will two closed points in the original space, okay, will remain closed in the PCA space after we project them onto the principal component axis? This is the first question. The second question, what is the difference between linear regression and PCA? Find a difference. Okay? Now, because here, if you look at it, it looks like you're fitting a line into the data, right? Like the line, the PCA line traverses the data. It looks like if we were to do like linear regression and these are our data, like data points, we want to fit a line into the data. So what is the difference? If you remember how linear regression works, you should be able to answer this because now you know how this works. Now, PCA, does it decorrelate the data features? So in the original space, you might have something like this, right? So this is what it means. It is decorrelated. It's correlated. So the features are correlated. And decorrelated, it means, you guys should know, so something like decorrelated is like something like this, okay? So this is decorrelated. These features are decorrelated. No direction. Direction is flat. This is, you know, positive correlation. This is negative correlation. This is flat decorrelation, okay? When it's flat. Decorrelation. Enhance the correlation between, so A, B, and C are similar, quite similar. So for the third question, you answer by yes or no. And it would be nice if you can draw a figure and justify why. Explain why, basically. Okay, one more minute. Okay, so first question, who says no? Okay, okay, okay. Right, so let's look at this question. Does PCA change the original data in terms of local structure? Let's create an example. So these are my points. Or maybe some. So if I So let's say, for example, this is the axis of maybe the maximum variance, right? Now, if I do project, these 2 points are close. What does it mean, local structure? It means my neighbors in the original space will also remain my neighbors in the projected space, okay? So here, if I do project these guys, you notice that they remain quite close locally, especially if they are very close. And local structure means local neighborhood, like your immediate, the close point. So for example, if I project these two, right? These remain close on the new space, right? Led by this axis, U1. Now, 2 other points, these 2 points. So if I project them, they're also close. And this point is far away from this point, still maybe within slightly local neighborhood. But then local structure means the neighborhood needs to be small. So this is a small neighborhood, right? This is a large neighborhood. And there's the global scale. The global scale means when you look at the whole data, like the relationship between this point and another point, okay? So on a global level, it might not preserve the relationships, but on a local scale, it does. So my neighbors in the original space, okay? So what is the original space? Let me just drop it. So this is the original space, maybe. Okay? 2-dimensional data. So if I am close to this point in this space, when I project onto the principal component, I'm going to be also close to this point. So yes, the answer is yes. Okay? You guys get it from the picture? Okay. Now, the second question is, what is the difference? Yes?
Does it change or not?
It does not. No, it does not. So
the answer is no.
Yes, the answer is no. Very good. So let me put the answer is no. Yeah, so does PCA change the original data in terms of local structure?
The questions have like
no.
opposite logic, but the 2 questions have opposite.
Yes, absolutely. Yes, they do. Thank you for noting that. Right, so here we go. Now
The first question is no, but the second
this is the
one
worst way of devising questions. Right, sorry about that. So let's answer them. Does PCA change? But it's a trick, so you can say yes and no. So does PCA change the original data in terms of local structure? So no. Will 2 close points in the original space remain close in the PCA space? Yes. You guys get that, right? Okay. Cool. Now, this one. What is the difference between linear regression or least squares and PCA? So the first difference is one of them is supervised, the other one is unsupervised. Is PCA supervised? What is supervised? That means we're using a score or a label to train the model. Okay, so when we found the eigenvectors, did you use any labels or scores? No, so it's unsupervised, right? We're just exploring the relationship between the features to find the covariance of the features, to find the principal components. So it's not supervised. Sorry?
It's not a learning method.
It is not a learning method, right? We're gonna use it for learning, but there are, yes, very good point. But if you look at it, here there are methods that do exactly dimensionality reduction in a supervised way. Okay, so they use the labels to find the best projection axis. That, like for example, linear discriminant analysis (LDA). So LDA is the supervised version. You can look at it as you can think of it as a supervised version of PCA. But generally, here PCA, if I give you supervised or unsupervised, it's not supervised. But we're going to use it for training and testing later on when we integrate it with a classifier. So it might get a bit clearer. So here, so basically, linear regression is like supervised, right? So this is one difference. The other one, it does not use any label, so it's unsupervised PCA. Okay. Now this is the one of the major differences. The second point, the B. So here, one minimizes the errors between each sample and the model line, and the other one minimizes the error orthogonal to the model line. So if you guys remember, in linear regression, what did we do? We want to find the best fitting line to the data that minimizes the sum of the least squares of all those distances, okay, to the line. So we want to find the best line that minimizes the sum of all these distances, right? So that's linear regression. Now, the difference between linear regression and PCA, that PCA, we are basically computing the projection, the orthogonal distance to the line, okay? So here, what we want to do, we want to minimize this distance, which is also boils down to exactly maximizing the variance. So the way I formulated it earlier is maximizing the variance of the projected points, okay, of our cloud. But here, it's what you need to remember that in this case, we are projecting each point. And here, it's a simple distance, okay? Right, so this is one main thing. So in this case, we are not projecting for the linear regression, okay? Any other things you guys thought about when comparing linear regression and PCA? Any other differences?
With PCA, we try to extract a new feature.
Yes, very good. With PCA, we try to extract new features, while with linear regression, we try to predict outputs from features. So it's kind of different. But here, this is one of the most, subtle, or confusing differences, because sometimes you might think that PCA is trying to fit a line into a data. If you try to program this using the same data set, okay, and you plot two lines, the regression line and the PCA line, you will see that they are different generally, okay? Now, the third question, does PCA decorrelate the data features, yes or no? Who says yes? Okay. Yes, it's a yes. Okay, so I will explain. So here, what we have, so it's a simple thing, right? So if we have our data is like this. So you can see it's positively correlated, right? This is in the original space. So let's say this is my original space, the axes, right? Then I do PCA, and look, guys. So this is my basis 1, and then I have my basis 2 orthogonal, so second eigenvector, right? And what do you guys notice? If I rotate it, now, if you look at this, okay, in this new coordinate system, U1 and U2, it's decorrelated. It looks like that, right? Decorrelated. If I were to rotate those, right, and put it this way, if I rotate everything, U1 and U2, and I plot my data, oops, and plot the data, so it will be something like this. So it is decorrelated. It decorrelates the data. This is very important. So PCA decorrelates the features, okay? And when doing the decorrelation, that's how it is able to find the most relevant information, or extract new representative and meaningful features. So that's a yes. Now the second one, enhance the correlation between data features. Does it make the correlation between features stronger? No. So if you said yes here, you should say no there, right? Now this third one, preserve the correlation or dependencies between features in terms of, it does not preserve, it decorrelates. So preserving the correlation, it means if I have a positive correlation of 0.7 here, I should have a positive correlation in the new space, projection space of 0.7. I do not, because here they are decorrelated, right? So this is a no. Now the third question, preserve the maximum variation or variance of the data. So yes, that's a yes, and that's how we actually found the axis. It's like we found it by trying to to basically the variance of the projected data. So this is a yes. Okay, you guys got that? Is it? Do you have any questions? If you have questions, let me know. If it's not clear, I can re-explain. So if it decorrelates, it means it doesn't make the correlation stronger. So this correlate, like these guys are decorrelated. So they have like it's a flat correlation. Okay, great. Now, so let's say what next? So what? So why we're doing all of this? Why we're finding these axes? Why we're doing PCA? What are the potential applications of PCA? Right?